All right, so we're back with lecture 2 here. Lecture 2, we're going to pick up where we were talking about organic chemistry, and now we're going to dive in a little bit into some review. We've got Lewis structures up first, and then we'll talk about atomic orbitals, and finally molecular orbital theory to help us explain some of the most important properties of different organic chemicals. But starting with, in the early 1800s, we've got to think we had very primitive chemical instruments at the time. If you recall from your general chemistry class, one of the things that chemists were able to figure out about a compound was its empirical formula. And then after some time later, they were able to identify some molecular formulas as well. And chemists started to notice that compounds that had the same empirical formula, and even if they had the same molecular formula, had different properties. One example would be ethanol, so ethyl alcohol. That's the drinking alcohol in beer, wine, etc. That has a boiling point of around 78 degrees Celsius. And there's another compound that has a formula of C2H6O. There's another compound that has the same formula, dimethyl ether. And that was isolated as a gas initially. So its boiling point was below room temperature. So people figured out that it's not enough just to have the formula or the number of the types of atoms to describe a compound. So the question, of course, why is a compound's formula not adequate to define it? It's because there are very important structural considerations. It's not just about the number of atoms, it's the way that those atoms are bonded together. So that's always an important thing to review here at the beginning of the semester. So as I mentioned already, dimethyl ether and ethanol, they share the same molecular formula, C2H6O, yet they differ significantly in virtually every other property. Ethanol is much more polar. Dimethyl ether is a gas. It's very poisonous as well, so consider that. Ethanol is slightly poisonous, but much better for you than dimethyl ether. So we came up with this rule where if you have two compounds that have the same molecular formula, but they're different, they're bonded in different ways, we call them constitutional isomers. So think about it this way, it's a constitutional, that's the way things are constructed, and then isomers, that means same molecular formula basically. So isomer just tells you that it's two compounds with the same molecular formula. I say this now and I try to explain it that way now because we're going to talk about several other kinds of isomers this semester. But the first one that we want to review is constitutional isomers. Okay, now I mentioned in lecture 1 that we talk a lot about carbon. That's kind of the central element here for our organic chemistry. And we also have to consider several other atoms that are going to be bonded to carbon, but focusing on really nitrogen, oxygen, hydrogen, and then the halogens. So things like fluorine, chlorine, bromine, and iodine. That covers, 99% of what we're going to see. Throw a sulfur in here every so often, but we're going to focus on these. So that's kind of where we want to start from this semester. Now, so this is also something that you're probably familiar with from before. We know that each of these elements has like a preferred number of bonds that it wants to form with other atoms. So carbon likes to form 4 bonds because it has 4 unpaired electrons, so it can form 4 covalent bonds. So we call it tetravalent. So it's like 4 bonding, the way you can think about it. Nitrogen, on the other hand, with 1 lone pair and 3 unpaired electrons, tends to form 3 bonds, things like ammonia and other compounds. So we call it nitrogen trivalent, 3 bonds. Oxygen, same deal, divalent, like in water, it forms bonds to 2 hydrogen atoms. And then finally, we have the hydrogen and the halogens, which are monovalent. They only want to form 1 bond. Now, you can force these to form more or fewer bonds in different scenarios, but we just want to keep in mind that this is where they like to be. This is where they're going to have a neutral formal charge. So very brief, we're gonna try to remind ourselves what a covalent bond looks like and what it actually is. So we're going to start with just remembering that a covalent bond is just a pair of electrons and it's shared between 2 different atoms. So for example, if you take two hydrogen atoms and you stick them together, as they come together, the electrons are going to form this favorable interaction. So here's our energy diagram. And what we're doing here is we're bringing the two hydrogen atoms closer and closer together. So here they start out far apart, they get closer, and there starts to be a bonding interaction that forms. And then finally we reach a local minimum here, or just an absolute minimum, I guess you could say. And this is where our bonding interaction is fully formed. So now the two electrons that were unpaired on either hydrogen atom are now fully covalent. They're shared between the two. Now, if you try to stick it any closer, now all of a sudden you have the two nuclei of the two atoms interacting with one another. So just keep that in mind, that this covalent bond is a favorable interaction between two electrons. So we're bringing two atoms together through this favorable interaction. Now, what is it about this 0.74 angstroms that's so special? Well, as we mentioned, this is where our bonding interaction is strongest. And that's because we have these attractive interactions between the negatively charged electrons and the positively charged nuclei. But we also have repulsive charges between the two nuclei themselves. We also have to consider the repulsive forces between the negatively charged electrons, but that's something that that's not really relevant in this scenario. Really, it's a balance between bringing the negatively charged electrons closer to the positively charged nuclei, and then the repulsion between those two positively charged nuclei. Okay, quick review. I hope you guys remember this, but it's always good to just state it one more time, get it in your minds before we dive into too much farther here. So remember, each atom has a nucleus that's in the center of it. That contains its protons and its neutrons. So the protons contain a +1 elementary charge and neutrons are neutral. And then we also have electrons. Those reside in orbitals that are outside the nucleus. Furthermore, within the electrons, we have core electrons that are close to the nucleus. And then on the very edge, on the outside, we have the valence electrons. Those are the electrons that are in the outermost shell. So like if we look at carbon, carbon is 2s2, 2p2, if we look at its electron configuration. So the 1s2 electrons, those are the core electrons. 2s2 and 2p2 are the valence electrons. So we would say that carbon has 4 valence electrons. That's going to be our focus because we really care about the valence electrons. That's what's going to do the bonding. The valence electrons are the outermost electrons. So when another atom hits another atom, the first thing that each atom sees is the outermost electrons, those valence electrons. Real quick, we can remember that we can, and we're almost always going to be dealing with main group elements, so the group A elements, or the representative elements, depending on how you say it. If you look at the group numbers here using the 1A system, you can actually just know the number of valence electrons using that. So group 1A has 1 valence electron, 2A has 2, 3A has 3, et cetera, et cetera, et cetera. So just keep that in mind if you ever need to know the number of valence electrons. Okay, Lewis structures. So we just want to review real quick how we draw Lewis structures. Lewis structures are going to give us the structural information that we need to know in order to predict different chemical properties, including the polarity of substances, and then moving on from there, the solubility of different substances, so how substances will interact with one another. So first up, the first thing that you want to do is draw the individual atoms and just put dots around them to represent the valence electrons. So for example, we have nitrogen here. Nitrogen is in group 5A. It has 5 valence electrons. So we give it 1, 2, 3, 4, and 5 valence electrons. So we predict we have a pair here and then 3 unpaired electrons in its valence shell. And then if we have hydrogen, well, hydrogen's group 1A, just 1 valence electron. Then what we have is, we know that we have NH3, so it's got to be this nitrogen bonded to the 3 hydrogens somehow. The way that we can form this Lewis structure is just by pairing up the unpaired electrons here. So hydrogen has an unpaired electron, nitrogen has an unpaired electron, so we're going to stick those two together. Same thing here, put that down here, same thing here for a third time. So that forms this kind of like interaction here. This is going to give us our Lewis structure where this is what our actual Lewis structure is going to look like. So now what we recognize is this nitrogen has a lone pair of electrons that are assigned just to it, and then 3 different covalent pairs with 3 different hydrogens. So hopefully you can remember, there's more complicated ways to do Lewis structures as well, but for the purposes of organic chemistry, it doesn't necessarily get that hard. There's many, many other things that get hard, but this is something that we can kind of take shortcuts on. Okay, so our first review video is going to be this sample exercise 1.2. I'm going to post this video as well on your Canvas. So just look for the sample exercise 1.2 video. And what we want to do with this video is try to draw a Lewis structure for formaldehyde, CH2O. Give it a try and see if you can make the Lewis structure for it. Okay, so before we're done with this video, we want to make sure that we remember one more thing about Lewis structures, and that is the formal charge. The formal charge that we find on different atoms is going to be a very important clue as to the reactivity of the compounds that we're going to study this semester. So remember, oh yeah, okay. If we have a negatively charged atom, that's an anion. Positively charged atom, that's a cation. I think you guys got that. We know that atoms in molecules are usually neutral, but they can have a negative formal charge or a positive formal charge, depending on how many bonds they have and how many bonds they like to have. So right, so what we're going to do is to figure out if we have a positive or negative formal charge, we're going to compare the number of valence electrons that the atom usually has based on the bonding pattern or the number of valence electrons that we count on the periodic table. We're going to compare that to the number of valence electrons that the atom actually has in the compound itself. So just for example here, this what we have is, it's the methoxide anion. I'll just tell you that right away. So this might be a structure that you look at here. So for each of these atoms, we want to go ahead and compare, we want to figure out the formal charge for each of them. So starting with carbon here. Carbon is in 1, 2, 3, 4 covalent bonds. We know that these 4 covalent bonds each represent 2 electrons, so it's 8 total electrons. And when we have a covalent bond, when we're assigning formal charges, what we're going to do is give 1 electron to each atom. So for example, this covalent bond turns into 1 electron for the carbon and 1 electron for the hydrogen. Now we can actually do a formal charge analysis for hydrogen. Hydrogen, group 1A, should have 1 valence electron. We check the structure. Oh, it's actually got 1 valence electron. So that means it's neutral. Carry on. We do that for carbon, hydrogen, and carbon oxygen bonds. The hydrogens, of course, are neutral, just in the same way that we just compared that for hydrogen. Now we look at carbon. Carbon is group 4A. It should have 4 valence electrons. So we counted up the electrons that we've assigned it. 1, 2, 3, 4. It does have 4 valence electrons. So that means, again, it's a neutral formal charge. So no formal charge to write on the carbon here. Finally, we have oxygen. Now, oxygen has 3 lone pairs here, so it's got 6 electrons that are assigned solely to it, and a covalent bond to carbon. So we're going to split that and give 1 of those electrons to the oxygen. Now, when we do that, all of a sudden now we have 7 valence electrons around the oxygen. Compare that to what we see on the periodic table. Well, oxygen is supposed to have 6 valence electrons. So if we have an extra valence electron that goes beyond what we expect, electrons are anionic, that's a negative charge. So we would say that this oxygen has a negative formal charge. So then what we would do is, and I'm just going to annotate this here for you so you can kind of see it, we're just going to draw a little negative sign here on top of this oxygen so that we see, oh, we've got a negative formal charge on this oxygen. So again, you have another sample exercise to work on with that. Just work on that with the main elements that we're going to see this semester. So again, carbon, nitrogen, oxygen, and the halogens as well. Okay, so now another thing that we want to remember is that that's how we assign formal charges. But there's another thing that we have to consider when we have covalent bonds, and that's that Covalent bonds doesn't mean that the electrons are shared equally between the atoms. We also have to take into account the electronegativity of the different elements. That's how strongly does an atom attract the shared electrons in that covalent bond. So there's a trend on the periodic table. Obviously, you'll always have this at hand, like when you're taking your test or something like that. We'll try to make it easy for you as well. There's really only a handful of type of bonds that we're going to see this semester. So determining nonpolar versus polar bonds is going to be relatively straightforward. But remember, the general trend is that it increases left to right across the periodic table, and then bottom to top up a group in the periodic table. The way I always remember it is just that fluorine is the most electronegative element, and then electronegativity falls away from there. Okay, so this gives us three different types, right? We have the covalent bond. This is going to be where the electronegativity difference is less than 0.5. So of course, if you have two of the same atoms that are bonded together, so carbon and carbon here, that's a totally nonpolar covalent bond. It's absolutely equally shared. The other type of bond that's really important is going to be the carbon-hydrogen bond. That has an electronegativity difference of 0.4, which less than 0.5. So again, that's a nonpolar covalent bond. These are going to be two of the most important bonds that we see this semester because, again, almost every compound that we see is going to have carbon-carbon and carbon-hydrogen bonds. And the only thing we need to know is that those are nonpolar bonds. It's not the only thing we need to know, but that's one important thing that we need to know. Polar covalent bonds, that's all of a sudden where we have this difference between 0.5 and 1.7. Kind of arbitrarily chosen, but you get the idea. The most important bond that we have here that's polar covalent is the carbon-oxygen bond. That's the one that we see the most this semester. There's also the oxygen-hydrogen bond is a polar covalent bond. Finally, carbon-nitrogen and nitrogen-hydrogen as well. Those are going to show up a lot too. Also, carbon bonded to fluorine and chlorine also end up being polar covalent. So just keep that in mind. Finally, if you have a difference in electronegativity of more than 1.7, that's when you have an ionic bond where now all of a sudden those electrons are not equally shared. They're assigned entirely to one or the other of the atoms. Okay, and we just kind of keep in mind, yeah, so this is what I was saying on this last slide here. This is going to be kind of our important understanding of covalent to polar covalent to ionic. The most important bonds, carbon-carbon, carbon-hydrogen, nitrogen-hydrogen, oxygen-hydrogen should be in here, carbon-oxygen. And then down here, basically anytime you have a metal bonded to a non-metal, that's going to be an ionic compound. So just kind of keep that in mind. Right, so occasionally, and this is going to be something that shows up later this semester, we will have lithium, copper, and sodium all show up, and also magnesium, excuse me, I almost forgot. Magnesium is the most important one, show up as drawn as like a covalent bond here, where you have carbon bonded to one of these metals. Well, that's one way to draw it, but what we really know is if we have this carbon bonded to a metal, it's really more like an ionic structure where both of these covalent electrons are really assigned to carbon, which is the more electronegative atom, and then the metal, lithium or magnesium, whatever it happens to be, is positive. It's a cation. So just keep that in mind. In this case, it's an electronegativity difference of 1.5. As I mentioned, it's a very flexible difference there. It's not an absolute ionic versus polar covalent. There's it's a spectrum is the way you can think about it. These things bleed into one another. So we're going to draw it this way. We're going to draw it this way. We just need to keep in mind that this is a highly polarized bond. Okay, and that concludes lecture 2. Make sure to check out the sample exercise videos that I'm doing as well. And I will see you in lecture 3.